हाँ हाँ, मेरा ख्याल में आ गया। ओके। अस्सलाम वालेकुम। जी अस्सलाम वालेकुम। अच्छा, मैंने वो वीडियो ऑन की थी, आपको नजर आ रही है उस पर जब मैंने की थी ऑन? या मेरा ख्याल वीडियो नहीं अलाउड है ना? अच्छा, क्योंकि मेरे सिस्टम पे शो नहीं कर रही, इस पे मैंने किया ऑन कैमरा, नहीं आ रही। आ रही है आपको? आ, हाँ, आपकी तो आ रही है, मेरी नहीं आ रही है ना, ये कैमरे का मसला है। ओके 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 ओके, नहीं नहीं, अब सही हो गया। ओके ओके ओके, ठीक ठीक। ओके, थैंक यू, समझ।
السلام عليكم دكتور دكتور خرام.
अस्सलाम वालेकुम। अस्सलाम
عليكم
वालेकुम डॉक्टर अली,
السلام.
हाउ
How
आर
are
यू?
you?
अल्हम्दुलिल्लाह।
I just want to make sure that things are working perfect. So
अल्हम्दुलिल्लाह।
I cannot turn the camera now because the host has stopped it.
ओके।
Uh, can you allow me to turn on the camera? I will also try to screen share. Just
Uh, uh, Dr. Adi, can you check now?
the camera.
Yes, I think,
Yes.
I have made you co-host, so you should be able to.
Okay. I'll just try the sharing quickly and then just. So just go to my PowerPoint. You can see the PowerPoint, right?
Yes.
Okay, so should I leave it like this?
Yes, Dr. Adi, I would appreciate if you can leave it like this.
Yeah, so because we didn't have to do it again.
Hello.
No?
Hi, Professor Tam. How are you?
Oh, good. No, oh, good. You can hear me. That's good.
Yes,
Okay.
yes. I just moved you into the panel list.
Yeah. I accepted already.
Yeah. So I will make you co-host so that you can share your screen during the talk.
Oh, okay. Yeah. Thank you.
Okay. Thank you very much. Well, I think it's time now. So maybe we should start our forum. Good afternoon, everyone. I'm Dr. Mohammad Zahid Khan, co-organizer of this forum. And on behalf of our committee, I would like to welcome you all, especially the speakers who have given their time to present their work in this forum. So as per the schedule, we will have 2 sessions, and then we will conclude with a short panel discussion. But first, I would like to welcome Dr. Adi Mokhebel, who is the director of the Center for Communication Systems and Sensing, to start the welcome talk. And this forum we have organized jointly with our Interdisciplinary Center for Communication Systems and Sensing and our Electrical Engineering Department. Dr. Adi, the dais is yours. Thank you.
Thank you very much. So, Bismillah ar-Rahman ar-Rahim. Assalamu alaikum, everybody. I'd like to welcome you to KFUPM virtually, and we will hope to see you physically. On behalf of the Vice President for Research and Innovation, Dr. Ali Sheikhi, I'd like to share with you the opening of the session, I would like to share his message as a starting to the session. Then in the second part of the talk, I will just shed some light on the center, the communication system and sensing center. So as we all know that photonics, optics represent the backbone for communication, and it's highlighted as the primary area that enables our societies to be resilient. Our today's forum is co-organized between the center and the E department. We have prominent speakers from international and national institutions that they're going to cover different topics, the three main areas related to photonics and optics, optical communication, optical sensing, and photonics integration. Now, the title for the forum, Optical Communication and Sensing for Next Generation Green and Smart Systems, suggests that the integration between communication and systems. So we expect future systems, designs, networks to be heterogeneous, flexible, intelligent. They are going to fuse both communication and sensing, fusing RF with optics, and the future will be kind of integrated system that covers all. So we have a hub of Internet of Everything. Machine learning and artificial intelligence, which is a topic that is invading all fields, and photonics is not an exception. This forum will also shed some light on the utilization of machine learning and AI onto these topics. At the kingdom level, at the Kingdom Saudi Arabia level, we know that there is Vision 2030, and which takes these topics of communication and sensing into account. Now the Kingdom of Saudi Arabia is the 10th or among the 10 best university countries in the world when it comes to the fastest internet access. And that's something that we are proud of. And also, as the importance of this topic, there's a new program, that's the Saudi Semiconductor Program, that is shed some light on the use of electronics and optics and manufacturing it locally. So this is at the kingdom level. When it comes to the university, the establishment of the center itself is a sign of the importance of the topic. And we have now a dedicated center for communication systems and sensing that integrates RF and optics into one center. Now, before I proceed and with the talk, I'd like to thank very much the prominent speakers, Professor Tam, Professor Alan, Professor Habib from Tunisia, and Professor Yaten, one from KAUST. We have speakers from Hong Kong, Tunisia, and Saudi Arabia. So you are most welcome, and we are happy to have you here with us, and everybody to learn from this forum. I leave later on the session distribution for Dr. Zahid or Dr. Khurram to explain the distribution of the sessions. But I'd like to thank them very much, Dr. Zahid and Dr. Khurram, for their efforts to make this forum possible. If I miss anybody also, so then I'd like to thank everybody whose pictures here or otherwise. Now, my next part, in few minutes, just maybe 2 or 3 minutes, I'll just shed some light on the center. So that will promote collaboration with others. At King Fahd University, we have about 16 centers. And as you can see, the Center for Communication and System is one of them. We have some sister or brother centers, including Center for Smart Mobility Logistics, Center for Intelligent Secure Systems, and others where we have direct collaboration with them. The center has mission, challenges, targets, right from communication to sensing. And we include sensing signal processing as a tool. Of course, we cover both optics and RF as media or spectrum for performing communication or sensing. I will share with you the link for the center if you want to read more, just to save the time for the forum, just shedding some light and highlighting the important topics. We have experts in communication systems, signal processing, optics, EM microwave, radar and localization, control, electronics, and we have some guest affiliates. Now, we also cooperate with different ministries, with different institutions within the kingdom and outside, whether communication or sensing-related institutions. 2 main challenges have been identified by the center, including the challenge which is related to drone, whether drone communication or sensing. Also, Dr. Zahid also is proposing projects related to the use of optics or laser communication between drones. So the one main challenge that the center addressed is all challenges related to the use of drone in communication and sensing. The second one is green sensing and communication, and that relates to the title of the forum, where we try to reduce the emission, we reduce the required power to operate these communication system and sensing, and that's why we call it green communication and sensing. Now, before I leave you with the forum, I just want to stick to the time. I'd like to urge everybody who's here to use this opportunity as a network. We have excellent professors at King Cloud University. We have excellent graduate students and postdoc, and we are lucky to have international speakers here with us. So I urge everybody to make use of this opportunity to gain knowledge about optical communication system, photonics, and its importance to our society. And I wish all of you a productive forum. So thank you for giving me the chance to be here with you. And I'd like to carry the message of the VVI, the Vice President, his thanks to all of you and his welcome message. Thank you very much.
Thank you very much, Dr. Adi. So let's kickstart the forum. So as we know, we have two sessions. So the first session, session one.
I stop sharing. Should I stop sharing?
Yeah, I think if you can stop sharing. So we have the first session, and I would invite Dr. Khurram Qureshi to take care of the first session in inviting the speakers. Thank you.
Thank you, Dr. Zahid. So I welcome you all for coming over to this KICS symposium. So we have a very distinguished list of panelists and the speakers today with us, and we're really proud of that. So let me first introduce the first speaker, Professor H.Y. Tham. So the Professor H.Y. Tham received his BS and PhD degree in electrical and electronic engineering at the University of Manchester, UK. Later, he joined Hurst Research Center, GEC Marconi Limited, London, working on optical components, fiber laser systems, and erbium doped fiber amplifiers. Professor Tham then joined the Hong Kong Polytechnic University in 1993 and is currently the chair professor of photonics at the Department of Electrical Engineering and the director of Photonics Research Center at the Hong Kong Polytechnic University, where he has established several world-class facilities. His current research interests include fabrication of special optical silica and polymer fibers and complete optical fiber sensor solutions for various industries, including railways, smart buildings, and medicines. Professor Tham has published more than 700 technical papers and been awarded more than 20 patents. He has extensive research collaboration with many renowned universities around the world. Professor Tham has extensive R&D collaboration with industry as well, and his team has installed many fiber Bragg rating sensing systems for railways in Hong Kong, mainland of China, Singapore, Netherlands, Taiwan, and India. His team built the first city-wide fiber optic sensing network-based monitoring system of for metro system in Hong Kong and Singapore. Professor Tham has also won numerous international awards for his inventions and is a chartered engineer of the Engineering Council UK, an IEEE fellow, and the fellow of Optical. Without further ado, let me now present our first distinguished speaker, Professor H.Y. Tham. So inshallah, today he's going to talk about the title that is From an Accidental Discovery to AI-Enabled Photonic Sensor Network. The floor is yours, Professor Tham.
Thank you. KK. Let me try to share my. Can you see the screen?
Yes, we can. Yes.
Okay, so are you seeing the right? You're seeing the slide,
yes,
right?
Yes, we can
yes,
see.
We can see the slide, yes.
Oh, okay. Okay, thank you. Yeah, first of all, I'd like to thank you, Dr. Ali, for the warm welcome. And of course, I would also like to thank Dr. Karashi for inviting me for this forum. Okay, so I'm H.Y. Tan from the Department of Electrical Engineering of the Hong Kong Polytechnic University. So there are many successful inventions, such as implantable pacemaker, POSIT nodes, and penicillin were discovered by accident. Now, optical fiber grating sensor technology originated from the accident discovery of photosensitivity in optical fiber. Now, photosensitivity enabled the fabrication of FPG, or fiber drag grating sensors, in optical fiber. Over the last 30 years or so, FPG sensors have been successfully used in many industries. In this talk, I will present our work in using FPG sensors in the railway industry, where we combine FPG sensor and AI technologies to build predictive maintenance system. Now, I will start with a short story of how photosensitivity in optical fiber was discovered by Professor Ken Hill's lab in Canada. This phenomenon allows FPG sensor to be created inside the core of standard telecom optical fiber. I will briefly explain the unique features of FPG sensors and the uses in many industries. Then I will introduce our work on using large-scale FPG-based sensing system for monitoring railway and building. Now, in an early experiment, Professor Hill observed that the optical power from an optical fiber decreased after a few minutes. He later set up an experiment as illustrated in this slide, where a 244 nanometer laser light was launched into a 1 meter long optical fiber. He measured the transmitted as well as the reflected optical power using 2 power meter. Let me bring up my laser pointer. Okay, so using an optical power meter at the output and also an optical power meter at the input. Now, after a few minutes, almost all the light was reflected from the fiber, and he observed that a permanent 1 meter long grating was created inside this optical fiber. Okay. Now, when the fiber is pulled, the reflected wavelength changes with the applied strain. Okay, so the grating could therefore be used as a strain sensor. So in fact, he have created by accident, okay, and permanent grating in the optical fiber, and this is a start of using an FPG sensor. However, the operation wavelength is restricted to the writing laser wavelength around 244 nanometer. Now, 10 years later, Gerard Mills used 2 laser beams to generate an interference fringe. Okay, as shown here. So this is an optical fiber. So the 2 beam from 244 nanometer laser, okay, and then split into 2 beam, and these 2 beam interfere, okay, inside the core and optical fibers. So this is a 1 photon process, which is much more efficient than the 488 nanometer 2 photon process used by Ken Hill. Now, this process is much more efficient, and it can write an FPG in an optical fiber in just a few seconds. More importantly, FPGs of any operating wavelength can be fabricated using this technique. The photograph in the center shows the core and optical fiber here, where an optical where an FPG was inscribed. Now, commercial FPGs are normally fabricated using the face mask technique, as shown in this figure on the right. Now, this is a much more repeatable process, and high precision optical alignment is not required when you're using this face mask to write a grating inside the core of fiber. Now, the grating of the face mask is imprinted inside the fiber core using this UV laser light. The fringe pattern in the FPG here, okay, is half of the face mask grating pitch. Therefore, we can write an FPG of any wavelength using face mask of the appropriate grading pitch. Now, this cartoon shows how FPG can be used as temperature or strain sensor. The typical strain and temperature coefficient of FPGs in standard optical fiber are 1 picometer per microstrain, or if you want to use it for measuring temperature, it is 10 picometer per degree centigrade. Okay, and so this simple equation, okay, determine the refractive wavelength, or what we call the Bragg wavelength, okay, when the refractive index in the fiber core or the FPG change, or the period of the FPG changes. So this animation shows that when you apply strain to the FPG, then the refractive wavelength changes as indicated by the different color. Now, one of the main advantages of this particular type of sensor is that all other wavelengths will be transmitted without any loss. So you can easily fabricate many FPG along a single fiber, as long as you make sure that all these FPG along a single fiber reflect a different wavelength. And you could use all these FPG to measure different parameter. So FPG is sensitive to temperature, as I said before, is sensitive to strain, but you can also, through some smart material or transducer, to convert an FPG to measure acceleration, vibration, or even CO2 gas. Now, FPG sensors have been successfully used in many industries. Some of the early applications are in oil and gas, aircraft, and large structures such as bridges and tall buildings. So let's look at the tower on the right. So this is the Canton Tower in Guangzhou, China, where in 10 years ago, we installed a structural health monitoring system, okay? The entire system actually consists of about 1,000 sensors, but they include 120 FPG sensors, which monitor stress, vibration, acceleration, inclination, okay? So just using fiber optic sensor, FPG sensor, we can measure all these different parameters of the 610-meter tall building. Now, more recently, FPG are used to investigate for their potential application in battery monitoring here, okay? So this is the work that I started about 5 years ago, collaborating with a few international groups, where we actually use an FPG sensor. Now this FPG sensor actually make a specialized optical fiber, where we actually fabricate the fiber in my lab, and then using this special fiber, some of the fiber are made of polymer, some are made of silica, and then we fabricate grating in there. Now the idea is we actually use the sensor, we put it inside the battery. When we use when the battery are in use, we can actually monitor all these chemical and physical processes happening inside the battery, okay? And that actually allows us to predict the aging of the battery. So we publish a paper in that, and that will become, I think, attract a lot of interest, because battery manufacturer, they would like to know, whenever they develop a new type of battery, they would like to know about the age, the lifetime of the battery. And using this technique, we're able to sort of like predict the lifetime of battery. Okay. And also recently we developed a special type of fiber, and then we make FPG, and we use it to monitor like the pulse width, okay, from the pulse width. This is actually a project I collaborated with a university in Japan. Using the single FPG sensor, we are able to determine the pulse rate, temperature, respiration rate, pressure, and even the blood sugar level. So just attaching it on the surface of the skin, it is able to give you all these sort of like vital information. Yeah. We also use it to build robotic scheme, and we use it to monitor the lift and escalator. Okay, I'll talk more about that later. Now, FPG sensors offer many unique advantages. I listed 3 of the most important ones here, and that allow the construction of an integrated large-scale sensing system The first one is a multi-point and multi-parameter, that is allowing many sensors on a single optical fiber to measure different parameters, as shown in the figures. And this is very difficult to do if you're trying to build one using conventional sensors. Now, different measurement would be required to measure different type of parameter if you're using like a MEM sensor or other type of electronic sensor. And then you have a difficulty of integrating all these different type of sensor from different manufacturers into a single system. And that can be very difficult or very expensive to implement. Now, FPG sensor EMI immune and no power is needed, okay, to power the sensors, nor the sensor network. Electrical power is only required by the interrogator. FPG sensors and optical fiber have very long lifetime and very low maintenance costs. And that's why we think that the FPG sensing network is actually a very green technology. A large photonic sensing network permits large amount of high quality and reliable data to be collected. This is not possible or extremely costly, as I said, if you're trying to use conventional sensor. And for example, electrical signal over long distances can be very noisy, and then you need a shielding. Okay, so the application of machine learning to big data and domain expert with a domain expert produce meaningful information. We have been collaborating very closely with railway experts for more than 20 years. We use the data obtained from FPG installed on rail track to generate health index, which is related to the health condition of the trains. So this is a sensor installed on the rail track, okay, to monitor all the passing train along that rail track. Now, the health index provides useful information and knowledge of the train. I will give some example in the later slides. Okay, so we have installed FPG sensing network in Hong Kong and Singapore to monitor the health of all the trains traveling on 5 metro lines in Hong Kong, as shown here. Okay, so this is referred to the smart railway system. Okay, where we install this actually monitor this entire line. Now, so we don't have to install FPG sensor along the entire length. Okay, what we have done is we identify a good section. Okay, so this is around maybe about 30 meter region, and then we install FPG sensor there. So every single train that passes through this metro line, we're able to monitor, okay, the health condition of the train. So it's a very effective approach. So we have installed one system here and one here. So altogether, we have installed 5 systems in Hong Kong, and they actually monitor, I think, probably about 80% or over 80% of all the metro train in Hong Kong. And in 2017, so 5 or 6 years ago, we actually also installed 2 systems in Singapore, SMRT. Okay, actually on 2 of the oldest line. One is this, the so-called north-south line. Okay, and the other one is the east-west line. Okay, so that's the complete system that we install in Singapore. So only this that require electricity, and then we have optical power going out from our interrogator to the different different part of the rail track. Yeah. So we have installed FPG on the rail track to measure the interaction between the track and the wheels of the passing train to actually get the health index of every single train that's passing on that particular line. Now, this slide shows the health index of an 8 coach train measured over a 2 years period. So this figure on the bottom right actually shows you the health index of one of the train, okay, for over 2 years. Okay, this is actually December 2014 all the way to December 2016. Now the red and the black dot represent the health index on the left and right side of the trend. Okay, every single coaches, every single coach are measured. Okay, so on the left here, actually what we have developed, we developed this color code system. When it's green, that means it's okay. Yellow, that means the health index is getting unhealthy. When it's red, that means it's very serious. Then we'll inform the railway operator, and then they have to look at this trend, and then we also show them where is the possible problem, or which critical component on the trend give you the problem. Yeah. Now the health index, if the value of the health index increase, that means the trend getting unhealthy, as can be seen by here. So over 1 year, okay. So the health index value on the left and the right side, and starting from about 0.5 and then go up to about 4.5 and 5. Okay. When they get to that level, then the railway operator have to take the train back to the depot and then do maintenance. And after maintenance, as you can see from here, when after the maintenance, they put the train back to the service, and our sensing system, okay, immediately detect the improvement in the health index. Okay, so we have obtained, I don't know, maybe many thousands of data like this, and the accuracy is actually 100%. So what I meant is that every time they have done some maintenance on the train and they put back on the track, and our system always show that there is an improvement, significant improvement in the health condition of the track. So this become a very useful system, maintenance system, because every single coach, we have this information. So that means the railway operator can use this information and then predict and schedule the next maintenance. So we have built the world's first predictive maintenance system for railway based on FPG sensing technology, using FPG sensor on the rail track to monitor the health condition of train. And we also install FPG system on the train to measure the condition of overhead line and rail track. Now the graph on the left, okay, show the rail condition along one entire metro line. Okay, so this is show you the health condition of the rail track along this. I think this is about maybe 36 kilometers. Okay, and then this system actually also use a color code. When it's green is okay. When it's yellow, okay, so that means the you start having this sort of like a corrugation is shown here. Okay, and this is common. So as the track is being used, and gradually the corrugation develops. Okay. Now the interesting about this result is that now you can actually, now normally this is actually inspected by visual inspection. So you have a technician, okay, maybe during nighttime, and then walk around the track, and when they identify this and it's too serious, then they were trying to sort of like schedule, so like a polishing routine, okay, to actually smooth out the surface. Yeah, but what we have seen in this particular incident, we can also, our system is also able to take the sleeper hotspot, okay, and this is not able to actually observed by a technician, okay, but our system is able to tell us this can be quite serious, because when you have a sleeper that is hot, so that means the vibration is very serious, and that can cause quicker degradation of your train. Yeah. I see that I only have about 1 minute left, right? So I'm trying to rush through this, and later on during the discussion, if you want to ask me a question, we can always go back. Yeah. So the overhead line, we actually collaborated about 7 years ago with Ricardo Rail in the UK, and we instrumented a single train. Okay, we put sensor on the pantograph, and we measure the contact force here. Okay, so they actually show here the contact force on this graph, and then we also show the result, the system also able to show the contact position. So when that contact, when you see it's moving like left, right, the contact point, this can be observed here. Yeah. So the idea is we want to make sure that the contact point between, this is where the pantograph collect current, okay, from the overhead line. We want to make sure that the contact point never actually move outside that, so like plus or minus 300 millimeter, okay? One is gone outside there. So this is the carbon collector is only limited from plus 300 to negative 300 millimeter, okay? And the contact force, they want to make sure that it's not too small and it's not too large. If the contact force is too large, then that means you wear out the overhead line very quickly, and it's very expensive to change the overhead line. So this is a very effective system, and then actually the result on the right, what I'm trying to show you is this is an incident that happened also in that year, 2015. So from the city center to the airport in the Netherlands. So the Schiphol airport is a very busy airport. And after we completed our experiment, and then a month later, there's an overhead line actually broke. And that actually caused a serious disruption to the passenger who's trying to catch a plane, obviously. And when we look back to our result, because we can actually see that 4 weeks before the incident happened, you can see it's very clear. And then 3 weeks, okay, before it happened, that particular contact force increased significantly. So that means this system using FPG is able to predict, okay, before an overhead line break. Yeah, 3 or 4 weeks in advance. And most recently, we actually using the same approach and working with a number of international lift and escalator company. We have to develop this system. Okay, so this is a system that also can do a predictive maintenance, and so it's quite a mature system now. We have actually over the last 2-3 years, we have installed over 100 systems in Hong Kong. And we even have this solar app, okay? So you can, I mean, the owner or the technician can have access to know the health of each individual lift or escalator. So all these are useful information. If there's something wrong, okay, or before something wrong happened, this can actually, this system can actually alert them. Now, Hong Kong have about 80,000 lift and escalator. It's probably one of the most, I think, city with the highest number of lift and escalator. And each of the lift and escalator are required by law in Hong Kong, okay, to inspect every 2 weeks. So that's mean it require a lot of maintenance work. And our system is able to reduce this amount of maintenance work significantly. So this is a result. So the white dotted line is indicate every two weeks, okay? So the results show the health condition of all the step roller of an escalator, okay? From like the first roller in this particular, if you look at the photo on your right, it shows the step, okay? These are the step roller. So this is a step roller. So our system is measuring the health condition of every single roller. So if you look at the step roller number 44, okay, green mean healthy, okay? So first inspection, second inspection, third inspection, fourth, and so on. So our system shows that there's no problem until around mid-September, okay? You start seeing this like turn into like yellow and then turn into red. And then the technician observe that and change it, and our system show that, and then it go back into green. So the 7 white dotted line are the days when inspection were conducted. The results show that at least the previous 6 inspections are not needed. Okay, so our system can definitely help to save a lot of manpower. Now, FPG sensor technology possesses many efficient features for large-scale sensor system. and is an ideal candidate for building the nervous system of a smart city. These include immunity to EMI, high bandwidth, and distributed sensing capability. So it's able to measure different physical and chemical parameters. It is a very green technology because optical fiber sensing system use minimum material, okay, to build a city-wide monitoring system, and no electricity is required, as I mentioned before. And another interesting feature is future-proof, because you can upgrade an FPG sensing system easily. All you need to do is you make sure that you attach a FPG sensor, but make sure the FPG do not actually have the same wavelength as the existing FPG. I think one example is particularly interesting is the recent strong uptake of EV, and that will result in the availability of terawatt hours of used battery, because EV batteries, after it's been used, and if it left about 80% of capacity, and you can't use it for EV, okay? So you're talking about a lot of energy storage potential for use, okay, of the second life battery, like 10 or 15 years from now. So an effective optical fiber monitoring system for used battery will become important in a smart city to ensure the reliability and safety of second life battery. So in summary, the amazing capability of FPG sensor to measure multitudes of physical, chemical, and biological parameters over long distances allow the realization of large-scale sensing network, and it provides an important green technology for smart city monitoring system. So that's my last slide, I think.
Thank you, Professor Tam. Thank you, Professor Tam, for such a nice talk. So is there any questions by the participants? If you have any questions, you can put it in the Q&A chat box. Okay, so we have a question. So the question is from Muhammad Al-Mubarak. He's saying, what AI model was used for prediction? Did you consider using graph?
Okay. Now, what we have used is now we developed this health index based on the measure result from all the FPG sensor. Okay. Now, so basically what we have done is we actually use the amplitude, and then we also look at the frequency content of this interaction between, for example, the sensor we install on the rail track. So the FPG sensor is actually measuring the interaction between the wheel and the rail track. Okay. Now, from the FPG sensor, the data we sort of like, as I said, you look at the amplitude and the frequency, and then we working with the railway engineer, and we develop a health index. Now, how we develop the health index, that obviously is a commercial secret. And then based on the health index, okay, and we use this machine learning algorithm to detect the abnormality of this health index. Now, because the amount of health index that we generate, well, the amount of data we get from FPG from every single day is about 1 billion. So there's a huge amount of data. Yeah. So the machine learning that we use is actually quite simple. Okay, just to detect the abnormal health index. Actually, I have an example that I didn't actually show just now. So as I mentioned before, in a normal trend, the health index of the left and the right, okay, should behave similarly. Now we have learned that if the left and right are behaving differently, then there's something wrong with the what we call the wheel balance of the trend, and this is not a desirable a feature of a trend. Okay, and then we can also now there are different behavior of the health index that indicate the different problem of a trend. Yeah. So using machine learning, we're able to learn that. Yeah.
Thank you.
So we basically just look at the abnormality of this health index and then the behavior of this health index. Yeah. Now the behavior of the health index, and if there's some problem with a different critical component of the trend, then the behavior of the health index are different. So basically what we have used the machine learning is very simple, because the machine learning actually learn the different behavior of the health index, okay, and then correlate that with the actual incident that happened.
Thank you, Professor Tam. Thank you, Professor Tam, for your answer. So let us move to the next speaker. So our next speaker is Professor Alan Pakta Lau. Professor Lau obtained the BAsc in Engineering Science and MAsc in Electrical and Computer Engineering from the University of Toronto in 2003 and 2004, respectively. He then obtained his PhD degree in Electrical Engineering at the Stanford University in 2008. He was the recipient of numerous government awards during his postgraduate studies at the Stanford University. He also worked at NEC Labs in America in 2006 as a research associate in Optical Networking Division. He later joined the Electrical Engineering Department in fall of 2008, where he's a full professor. His research interests include system design and signal processing techniques for coherent fiber optic communication systems and multimode fiber communication systems. Professor Lau is a senior member of IEEE and OSA called Optical now, and serves as a reviewer for many prominent journals, including Optics Express, IEEE Transactional Wireless Communications, and Transactional Communication. So let us welcome Professor Lau. So the floor is yours, Professor Lau.
Hello, Dr. Kurishi. Can you hear me?
Yeah, we can. Yeah, thank you so much. Yeah.
Okay, all right, thank you. Let me try to make sure I can share the screen. Are you seeing the screen?
Yeah, we can. Thank you.
Okay, good. Thank you, Dr. Kurishi, for your kind invitation and introduction. Thank you, the organizing committee, for this opportunity to share with you some of the work that we have done in recent years, particularly in the machine learning applications. So today I'd like to extend a little bit and talk in more general terms how machine learning is applied in various places in optical communications and networks. So let's start by talking about some basics. What is machine learning? So so by now I guess everyone knows about machine learning, at least qualitatively. So basically it is to train machines, algorithms, computers to learn from data without being explicitly programmed. Okay. Fundamentally, it is about pattern recognition. There are typically two types. One type we call data classification. So given two classes of data, how do you distinguish them? Another type is regression, basically of fitting a curve. Okay. Machine learning generally performs exceptionally well, particularly when you cannot really explicitly describe the underlying physics or mathematics of the problem that you are interested in. So I do communications, and I like to argue that before this wave of interest in machine learning, which sort of is a big thing since 10 years ago, we are always doing classifications and regressions to some degree. Okay, so for classifications, the standard in a standard communication setup, we always have received signal that we need to decide whether a bit 1 or bit 0 is transmitted. Okay, so we do this sort of decisions all the time. So what you see here is a standard what we call QPSK constellation. It conveys 2 bits. Regression, we also do this all the time. Any time when you have to estimate any parameter of a channel or or some parameters that describe a block of signals. Okay, in here is example of how we typically estimate the phase of the lasers. Okay, and so these sort of process essentially are curve fitting. Okay, so it is regression. So the point here is that a lot of the stuff in communications, not just optical, general communications, have involved classification and regression. Okay, long time ago, before anyone talked about machine learning. And so therefore, one of the important things that we felt we need to highlight is, first of all, what kind of problems in modern day optical communication networks that really need machine learning beyond the classical, beyond the typical classification or regressions. So I'd like to provide some simple examples to illustrate the point. Let's say we just talk about classification. Okay, so let's say you have this sort of data. Okay, so to classify them is pretty straightforward. Okay, so this red line is the decision boundary. Okay, so you don't call that machine learning. Okay, if your data looks like that, your classification boundaries would look like this straight slanted line. Okay, in terms of the algebra, what you actually do is you have to x and y coordinate. Okay, what you do is you actually rotate your coordinates and translate, put the red line, shift it towards the origin. Okay, and then you make a decision. So mathematically, this is a matrix W times x plus b, and then you do a decision on it. Okay, in machine learning language, you call it activation function, but essentially the idea is decision. Okay, you still don't call that a neural network. All right. However, if you have a problem that looks like this, okay, so what happens? It's that you have your x and y coordinates, and then so you first pass through this red decision line, okay, and then you pass through this blue decision line. Now, what you want to extract is the green portion, and then so what you do is you actually have an additional layer of decision to sort of single out this green area. Now, it is this sort of problem that naturally resembles the simplest sort of machine learning structure. In fact, the most common artificial neural network structure. Okay, so the point here is that the problem that you need to deal with has to be at least this complex in order for you to bring out machine learning. Okay, so now coming back to with that in mind, I want to come back to communications and networks. Okay, what sort of problems in optical communication networks will need machine learning? Typically, there are two types. Okay, first type is when we cannot explicitly statistically characterize the input-output relationship, or when the solution space is too big to evaluate one by one. So that's the general idea. Now, in more specific terms, here are the few areas that we have seen a lot of machine learning activities. First, it's what we call non-linearity compensation. So the idea is the fiber channel is not a linear system. It's a non-linear system. So in that case, you cannot really throw all the standard communications knowledge into a fiber channel. Okay, you need something more complicated. Another area is called optical performance monitoring. Okay, so the idea is to extract a small part of the signal somewhere along the network, and you try to infer the state of the signal, whether it has a good signal to noise ratio, or able to estimate some link parameters based on this small extraction of the signal. In a more network area, people are using machine learning to try to monitor the different parts of a network to sort of hopefully extract some fault detection so that you can do prevention. So this is quite universal. The philosophy, the idea is the same as the train monitoring that you have just heard by Professor Tam. So the idea is you use machine learning to monitor different parts of the stuff that you are interested in, and then try to extract warning signals before a major disaster happens. So that is exactly the same philosophically in optical network management. And then a more active take on such capabilities is to have what we call dynamic network configuration, where you real-time monitor the network state, and then you put the higher speed signal that caters for the real-time network condition to maximize the capacity. Okay, so I'll talk about these four areas briefly in the remaining time that I have. So I first talk about fiber nonlinear compensation. So this is something that we have done like more than 10 years ago. We like to argue this is probably the first work on using machine learning on fiber nonlinear compensation. So the idea is you have some received 100 gig received signal, QPSK signal transmitted over a long distance. Okay, so you recover the signal first, and then what you do is you first compensate the linear impairments. In fiber, the linear impairments is typically dispersion, chromatic dispersion. Okay, afterwards you put that into we put that into a neural network. Okay, and so basically it's a very simple one-layer artificial neural network, one hidden layer artificial neural network, and then the graph here are the performance results. So basically it is a Q factor versus launch power. The Q factor is a measure of a signal quality, and you can see that our method, of course, outperforms the case when you don't try to tackle the nonlinear effects. Okay, it is also comparable to a standard non-machine learning technique called digital backpropagation that tries to undo the nonlinear effect. So the advantage here is that the machine learning approach can give a performance similar to the best algorithm out there, but yet it is actually a lot simpler computationally. So since then, there has been a lot of other works that also try to tackle the problem from different angles. Okay, so there are work by a group in US, another work by a group in Europe that tries to use different types of machine learning methods to try to come up with highly specific decision boundaries for high-speed signals that have undergone some nonlinear effects. So you can see that your received signal distribution is quite distorted. That's because of the fiber nonlinearity. And because of that, it naturally calls for some machine learning techniques to try to develop the best sort of curved decision boundaries to maximize the performance, measured in terms of the bit error ratio. And in fact, there are works that tries to model this whole nonlinear compensation algorithm as a big neural network. So in this area of optical communications, all these approach to try to mitigate fiber nonlinearity, we can see this whole algorithm as a neural network. And in that case, we try to optimize all these parameters using standard machine learning techniques. Okay, so there are different groups, including our group, that sort of shows how much you can improve your performance by just taking a standard algorithm for nonlinear compensation, view it as a neural network, and then use the standard machine learning tools to try to learn all the parameters. Okay, and so besides fiber nonlinearity, there's also other types of nonlinearity in optical communications. For example, the oldest type of optical communications is what we call intensity modulated direct detection, IMDD. Okay, so that itself, it's also a nonlinear channel. Okay, so there are another bunch of work that tries to apply machine learning techniques to try to see how do you best design your signals, how do you best detect your signal using machine learning techniques. Okay, so typically what people have found out is that these machine learning techniques generally would give you a performance that is comparable to the literature, but they are generally simpler computationally. Okay, and this is a very hot ongoing area with lots of new ideas in every conference every year. Now, another application areas of machine learning in optical communication and networks, it's this thing called optical performance monitoring. So long story short, the idea is you extract a small part of the signal somewhere along the network, and you want to monitor the health or the status of the signal and the link. Right? So basically, you get a small part of the signal, and I want to know all the signal power, the signal noise ratio, these physical parameters, dispersion, portion mode dispersion, and then all the wavelength shifting, everything that you want that you can possibly extract. Okay, and so this is originally intended for ensuring the network is operating reliably. Okay, but these days we also take that in a more active role to try to tailor a custom provision, a custom-made light path. We put some light path on the network that is specifically tailored for the channel condition at that moment. Okay. So to just give one example of how difficult it is if we don't use machine learning. So one of the simplest or typical system setup for this application is that you can extract the signal amplitudes using some low speed component. Okay, you can have a distribution of all these signal amplitudes, and then the task here, I want to extract what is the signal to noise ratio and all these other physical parameters. Okay, so just if you wanted to do this job analytically, it is pretty much impossible just from this distribution and map to this data. Okay, but if you do a bit more empirical work, you can sort of see how each of these physical parameters, okay, somewhat depends on the different order moments. The first order moment is the mean of the mean. The second order moment is kind of a variance. Third and fourth order moment, it actually somewhat depends on different moments of this distribution. Okay, and so we don't know, or it's hard to derive how to map these physical parameters with the empirical moments. Okay, and this is why it is a very standard setup for machine learning. Okay, so you know that there are some dependence between the empirical moments and the parameters that you want to measure, but you cannot really analytically derive it. So that's exactly the perfect setup to use neural networks. Okay, that is what we have tried to do. So the input of a neural network is the empirical moments obtained empirically, and then I want to map it to the physical parameters that I wanted. Okay, and we can show that this way of doing things, we are able to achieve very good accuracies. And the point here is that this is something that probably you are not, most likely you're not able to do analytically, starting from this empirical distribution. It's virtually impossible, and that is why machine learning have found a good application in this area. Now, and since our work, there's also a lot of other approaches to try to use other features of this optical signal to learn the parameters. We've used amplitude histograms. There are people who use the eye diagrams as input. There are people who actually use the signal spectra as input. There are people who try to use the whole coherent detector signal as input to try to map these inputs with the physical parameters. Okay, and so this is again another area that we see a lot of machine learning activities. Okay, so now let's switch gear to talk a bit more about networks. Okay, so in optical networks, a lot of people talk about future networks need to be intelligent, autonomous, and dynamic. Okay, there's a lot of terminologies to describe the same thing. Right? Software-defined networks, automatically switch optical networks, zero-touch network, meaning you don't have to have any manual intervention. The whole thing can learn, monitor, and learn itself. Okay? Big data analytics, etc., etc. Okay, so these sort of things has been talked about for decades. But then nowadays, with machine learning, we are one step closer, because machine learning can help in the following way: forecast traffic patterns, okay, so that you can have a better resource allocation, and then intelligently commission light paths, incorporating the real-time physical layer condition to maximize the network throughput. And then again, as we briefly mentioned just now, predict physical link conditions for proactive fault detection. So real-time monitor the condition of the system, and then when it start to not behave, you immediately address the problem, so that you can ensure the network is operating correctly. So in this aspect, generally, one of the big enabler for this whole grand vision is to build some applications in the network monitoring software to try to estimate the what we call the quality of transmission of a particular link. Okay, so for example, I have a new connection request. I wanted to know whether this path can have a good signal to noise ratio, or whether that path is not good enough, or whether this third path have a good enough or bad enough signal to noise ratio to support this new request. Okay, so we call this quality of transmission. So generally, the way you do it, it's you take the input, the input of your QoT estimation. It's some link level parameters, like how many links you have, the length of your connection, and then the amplifier parameters, and then the so on and so forth. Okay, and so the idea is, again, you have this input features that mostly coming from the link description, and then you want to map to an output, either it tells you whether the supported SNR can support this connection request, or it outputs the estimated SNR of the channel at hand. Okay, so this again sounds like a standard machine learning sort of neural network sort of setup. Okay, and so there are a lot of people who work on it. What we are showing here is a group in Portugal that tries to study different sort of neural network topologies, and then the idea is you have these link input features as input. Okay, and then the output is to see how accurate it is to correctly determine whether the output has the enough SNR to support this connection request. Okay, and so we also try to make some comparison. We did a comparison between using analytical models and machine learning, right? Because these sort of areas is sort of gray area in terms of determining whether machine learning approach is better or traditional approach better. So both approaches will have their pros and cons, and then so we have shown in more detail, which conditions would favor machine learning, which condition would favor analytical models. Okay, so it's always a trade-off between how much accuracy you need about your parameter, your channel parameters, and then the computational complexity, how complete your theoretical model is, whether you have the right data set to train your machine learning if you want to go machine learning, or also even if you have a good trained machine learning model, how confident are you that this model can work in some other links or some other networks? Okay, so all these stuff are still ongoing discussion in the field, and it's still a very active area. Now, lastly, with all these advances in trying to real-time monitor and estimate the channel quality of networks, the last step is to actually provision or build or start new connections based on the actual real-time monitored channel quality. And this is one of our joint work with University of Bristol back in a few years ago. Is the first field trial demonstration of using machine learning in real deployed networks. Okay, so the idea is, again, your input is some link parameters, and then the output is the estimated signal-to-noise ratio of the link. Okay, and then based on your estimated signal-to-noise ratio, then we transmit different types of signal with different bit rates. Okay, and so this is a field trial, real demonstration of how we can actually make that happen in practice. And since then, there has been a lot of other trials to try to step by step make this a reality. So lastly, we talk about a little bit about proactive solve failure. Okay, so the idea is that we can actually use machine learning, monitor different link components. For example, monitor the input current of optical amplifier, or the inputs of the input current, and then also the temperature of the different components, and see if things are starting to go outside their normal operating range, and then in that case recognize the problem before major problems appear in the network. Okay, so in this area we talk about what we call proactive fault management. Okay, whether you can detect something is starting to be problematic, whether you can detect it is something that is imminent, or some problems that are slowly degrading. We talk about whether you can localize or find out where exactly the problem is, and then finally, what exactly is the problem. Okay, so I'll just give one example of a work done by Ever Networks company in Europe. So you can just monitor the received optical power. Okay, and then when they go away from this to the typical value, depending on the trajectory of the power evolution, you can actually classify there are different type of problems. So for example, if it suddenly goes up and comes back down, it is one type of problems. If it is going up slowly and then coming down abruptly, that's another type of problems. And they were able to sort of learn from these power waveform evolution to map to different types of problem, and then they will be able to identify the problems up to 96 hours in advance. And so that actually is a big advantage for network management. Okay. Yeah, and so lastly, so I just want to make a point saying that in a lot of applications of machine learning, the important point is actually to find the right data for training, less about finding the right model, because in the computer science community, most of the focus is on developing better and better models. But then when you apply to some particular disciplines of engineering and science, a lot of times the more important thing is to find the right data. The model itself might not need to be that fancy. And yeah, and so I think I'd like to conclude by saying, this area of optical communications, it is a combination of a lot of solid physics foundations and also a lot of math. Okay, so machine learning it's not a game changer, but it is actually a good complement to a lot of stuff that we already know from the underlying physics. Okay, so we are seeing more and more of these applications of machine learning in all different types of areas in communication and networks. And so again, there are a few areas that we talk about: nonlinear transmissions, performance monitoring, physically aware dynamic network provisioning, fault detection, and there's another area, channel coding, that we are not able to talk with the limited time. And so in the physical layer, this area, a lot of times these machine learning algorithms are alternative to existing algorithms, and then we are still trying to learn how well it can apply to different settings and how well it can save the computational time. For network layer, we sort of see its potential, but the integration of good model and good data set for training is something that people are still working on. Okay, So I'd like to conclude here. Thank you for your time. We'll be happy to take some questions if there are. Thank you.
Thank you, Dr. Lau, for your presentation. We have a question from Muhammad Al-Mubarak. He's asking, when performing machine learning modeling for compensation, is it necessary to continuously feed new data to retain the model, since the behavior may change as a result of different factors?
Yes. So far, the majority of the machine learning studies for compensation, it's on static environments where you're trying to compensate some static effects. For dynamic effects, right now, the approach is to try to still tackle the dynamic effects using conventional ways. Because again, one of the features of applying machine learning in optical communications is that the optical communication, or communication in general, it is built on a lot of solid math and physics. So we actually have a lot of tools to tackle those impairments. So so the question becomes, how do you best combine the machine learning, the new sort of thinking, with the existing, the traditional approach, which are actually very, very high performing. So you cannot just discard like half a century of work on those traditional algorithms. It's more about how you can best combine the traditional thinking with the new tools. So at this moment, the dynamic stuff, it is still more convenient and more approachable to use the traditional methods. And then you combine it with the machine learning stuff. Yeah.
Thank you. Thank you, Professor Lau. Thank you.
Thank you.
So let's thank our speakers now. And with this, we conclude the first session of our symposium. And we move on to the next session now. And Dr. Zahid will chair the next session. So over to you, Dr. Zahid.
Thank you very much, Dr. Khurram. Let's kickstart our second session. So we have our first speaker of the second session, Professor Habib Fatada. Professor Habib, he got the PhD degree in electrical and computer engineering from Laval University, Canada in 2001. And he currently holds several teaching and research positions in electrical and computer engineering with Laval University. He was here in King Saud University, and currently he is in Carthage University, Tunisia. And he was the founder and the CEO of Access Photonic Networks in early 2000, and the co-founder and the executive director of CACT's TIC for the E-Society, RFtronics, from 2010 to 2017. And now currently he is the founder of Idea Laboratory, University of Carthage, and professor of ECE with the University of Carthage. And he is the senior member of IEEE. So welcome, Professor Habib, and he's going to give us a talk or a sort of shedding light on the wave and the medium engineering driven by human and or artificial intelligence. Professor Habib, the dais is yours. So we will have around 25 minutes for the presentation and maybe 5 minutes for the question and answer session. Thank you.
Hello, Dr. Zahid. Hello.
Yeah, we can hear you.
We can hear you.
Oh, good, excellent. Okay, so do you see my screen?
Yes, we can see your screen.
Perfect. Okay, just a few moments to, okay, good. Bon, صباح النور, السلام عليكم, tout le monde, everybody. Okay, I am really very happy and honored by this invitation and this participation in this very interesting topic at this very nice morning. I am in the morning, still in the morning now. So I know in KFU PM maybe it's quite in the PM. I really appreciated both of the presentations, so both talks. Let me, okay. Okay, though, I would like to thank Professor Ali, who introduced the welcome for his warm welcoming at the beginning, and the organization committee. So Dr. Muhammad Zahid Khan and Dr. Khuram Qurashi, both professors are, I know both of them and collaborated since long time. As you said, Dr. Zahid, I spent some years in Saudi Arabia in King Saud University, and I've been honored for that. Really, what I will do in this presentation is to give a kind of survey of these activities, or my activities and activities of my team during the last decade, and try to. So I appreciated too much the presentation first by Professor Tam, who started his presentation by I have some souvenirs in my in Canada with the setup of the Professor Hill in the invention or the discovery of the Bragg gratings, and I worked in quite similar setups in making Bragg gratings over fiber. So I really very appreciated it, like close to 30 years ago. And we have used this kind of setups for many times in Laval University in the Center of Optics, Photonics, and Lasers. And we fabricated a lot of fiber Bragg gratings, and I will go back later. And also I appreciated a lot the talk of Professor Alan, who really brought the features of the machine learning in different applications that myself, I worked in these applications before, and you will see in this presentation, but without machine learning, because we worked on that a few years ago. So the machine learning and artificial intelligence is bringing a lot to the optical communication, optical sensing, and is bringing a lot to humankind in general. So I will go to, so my presentation will, it's kind of combination. I will navigate between two sets of slides. Some of them I will start about like introducing some of my actual activities, and specifically so okay, as Dr. said, Dr. Zahid introduced me. So I am professor in computer department. I am also advisor of the Minister of the Higher Education and Scientific Research in Tunisia, and director and founder of the Idea Lab, and also former co-founder of photonics for the society. So, and Idea Lab is we choose that name to which is like acronym for Artificial Intelligence and Data Engineering Laboratory. Artificial Intelligence and Data Engineering, as Dr. Lam said, it's okay. It's applied everywhere now, and maybe you'll see I choose this slide for the motivation. I am used since years and years to use the growth of the need of data bits, the need of bandwidth to support services. But really, what we need now, okay, should maybe close this. Okay, what we need now is what I wanted to say by this slide, Web 3.0. What Web 3.0 is the becoming wave of services which are developed around a human being and the human-centric services. When we talk about Web 3.0, we talk about semantic instead of syntax. The semantic of the words we pronounce, the semantic of inside the music, inside the films, inside the data, 3D data. We talk about also, so this is a new age of the web, which will carry all the services, okay, all these services, but below that services, we need an infrastructure, and this is the infrastructure that needed by photonics and sensing. Okay, so data protection today in Web 3. Today in 2.0, we have syntax-based web. We have the data. Our data is not protected. It's monopolized monopolized and is just given for free to Google, Facebook, etc. It's centralized in that companies. So the future should be decentralized, and we start observing this kind of generation of Web 3.0 with the decentralized structures and decentralized solutions. So people in the future, based on Web 3.0, will own their data and will protect themselves their data. They should have the machines or the spaces in the cloud to protect their data. This will be based on blockchain technology, and this will be the opportunity, or they will exploit at maximum artificial intelligence and machine learning. Based on Web 3.0, we will be able to make 3D for everybody, 3D cinema, 3D services, virtual, augmented, mixed reality, consensus based on the not centralized proof of work, but consensus proof of work, and so on, so on. So I choose this slide in order to change the way we are used to motivate people in working on photonics and in communication networks. Okay, this is the traditional slide to say, okay, so we need bandwidth. Okay, since we were studying in our master and PhD degree, we use the same, but we have been like 2G, 3G now for the 6G, but the issue is always the same. We need to make more advanced services with high value added services to people, and we need bandwidth. So we need networks, and to make that networks, we need devices, and we need photonics, we need radio frequency, and we need terahertz technologies, etc. And issue about cost. So what kind of applications we are interested in? So I think most of the people around the table are used to see this kind of slides that, we talk about smart systems, smart cities. We talk about Industry 4.0. Now we pass to 5.0. Internet of Things, Internet governance, multi-parameter sensing, 5G, 6G, physical layer. All this physical layer we are used to work on, and both of the talks in the beginnings, they covered too many corners of this physical layer. But I wanted, when I suggested the title of this talk to Dr. Zahid, I wanted to bring more thoughts about how to deal with, we are used to use pure or 100% a human-based intelligence to make our research and make our findings and find applications of our results, etc., etc., etc. So how this artificial intelligence, it's a multidimensional artificial intelligence that could bring, how we can bring together this human and artificial intelligence. Really, I don't have answers, but I have like questioning myself and questioning the audience and questioning my colleagues in the panel. But the second presenter, the second talk, presented some aspects, but artificial intelligence is really bringing a lot and impacting our life in everything, in almost everything. So this kind of thoughts. So let's say if I look to this fiber, what is this? Okay, at the right is looks like normal fiber core, cladding, coating, etc. And special multiplexing structures. So we did a lot. We have used our human intelligence to increase the density of cores, density of wavelength channels, density of now few mode fibers or on mode fibers. Now in the vortex channels and OEM channels, we use all this was like kind of inspirational. Do we think that artificial intelligence will bring inspirations also for us? So at the left, what I presented here is a very simple refractive index profile. If you look at this, very simple shapes, okay, very simple mathematical functions. Okay, you can see the square functions, the rectangular functions, the kind of Gaussian function, inverse Gaussian function, and these are used inspired by what? All of these functions, myself, I have used inspired by the duality we have learned in our undergrad courses about Fourier transforms from the time domain to the frequency domain, and other Fourier transforms from the time domain to the space domain when we talk about interferometric phenomena. If I come back to the presentation of Professor Tam, when he presented the beginning of the creation or the discovery of the Bragg gratings, it was an interference between two mathematical functions, kind of sinusoidal functions, and this interference, there is constructive and destructive interference. So mathematically, it's very simple functions of sum or superposition of two sinusoids or something like that, and we superpose also in the Fourier transform or let's say in the frequency domain or in the space domain, we make a result that is basically we are playing with a few mathematical functions to navigate and transfer ourselves from one domain to another. Time, frequency, space is all about this. And basically I am publishing papers since 20 years or more, is about I am using the same ingredients, applying them in different applications. The Bragg grating, when started, is just at the beginning is an overlap between two functions, two very simple functions, overlap, superposition, square function and sinusoidal function. And we did a lot of Fourier transform, inverse Fourier transform, and Z transform, and other kind of transforms also to discover different shapes of Bragg gratings. And we have optimized the performance of the Bragg gratings, and we have made the Bragg gratings for WDM multiplexing and demultiplexing, and also for sensors, as the Professor Tam introduced it, for sensor time, for frequency, for temperature sensors and stress sensors and pressure and other applications. And all of them we have used, let's say, basic human inspirations. And now we use machine learning, as introduced by the second talk, to improve what we have been doing. But the future is, I expect a lot of change in the future. So I expect this kind of artificial minds around us, like we are making a research group based on some artificial intelligence robots, and we are working with them and we are getting their ideas and implementing, etc. And I will appreciate that in the discussion period we talk about this kind of things. This is also raised cosine function. I learned that from the basic signal processing and signal transmission techniques, raised cosine function. I think my group have been the first to introduce that function. We brought this function from the signal processing, the filtering technologies, etc., We brought that and we applied that in fiber optics, and we designed novel fibers based or inspired by these raised cosine functions. We did also for Gaussian functions. And in the last, in the next slide, okay, raised cosine, inverse raised cosine. We used that for single mode fiber modified or multi-mode fiber or OEM fibers, this kind of OEM fibers. We are also using these inspirational simple functions. This is tangent hyperbolic. We have been also, our group have been the first to introduce this function. Okay, we did not create that. This is a Pythagore function, trigonometry Pythagore function, invented since or created since thousands of years. Okay, but we used some features of that function to say, okay, I think this is probably we apply if we make fibers and profile of fibers or profile of gratings of to improve that feature or to have these kind of outcomes and the performance. So it's kind of inspirations. So this is the tangent hyperbolic, the derivative of tangent hyperbolic, etc. And we made fibers, and we got the result. The results we have expected just by intuition, and even better than what we have expected. This kind, we made many publications out of that, and it's all driven by some inspiration. This is also inverse hyperbolic tangent fibers. And I could say that maybe most of my works, okay, and the contribution of my team was around that. And here we use also the basic characteristics of Fourier transform, inverse Fourier transforms, all this mathematical background to get how to say to concentrate the power in a specific direct functions, P1, P2, P3, P5, direct functions. We create direct functions as perfect as possible. And we use that, this P1, P2, we use that just to monitor the temperature, monitor the strain, etc., using our fiber sensors, not break rating in that case, but the specialty fibers. We play with the refractive index, and we use the features of these traditional functions, and we arrive to get really, so we play with the parameters of these functions, the curvature, etc., and we get these P1, P2, these peaks, okay, these peaks spaced, more spaced, or more closed, or correlated, or uncorrelated, etc. And then we take, for example, P1, and we observe what is the sensitivity, how this moves when I change the temperature, I change pressure, I try to make decorrelated behavior of these P1, of these peaks, etc. And all is inspired by mathematical functions, by signal processing, background, etc. Quantum communication, maybe the time allocated is not, we are also trying to do the same thing to make a quantum fibers and quantum sensor, quantum based sensors in that case. But inspiration, because the quantum world is quite different from our quite very physical world, or very high let's high dimension world, something like that. But quantum world is very different. So inspiration, by inspiration to get things, it takes a lot of effort, and we are doing some work on that. This is the potential of quantum sensing, quantum-based sensing, in too many applications, for sure, including the applications that Dr. Tam introduced it in the beginning, like the train positions, or the behavior, or the corrosion in the train, or the sensor of accelerations, for example, for towers or for different applications. Most of these applications are very well, as presented, are very well mature, okay, because also of an ecosystem of industrial ecosystem and business ecosystem that is in interaction, in continuous interaction with research communities. If you look here, most of the the work we have published. We are like in a research, applied research mode, but we have delivered some prototype, developed some advanced prototypes, but it's very difficult to go to the level of industrialization because it takes the whole value chain. So we are more concentrating on like preliminary value chains, but preliminary segment of the value chain. Okay, so I cannot do better to introduce machine learning for optical communication, etc., because we got very, very nice presentation just a few minutes ago. This kind of antenna design also, this is very nice application. This is one of my former students. He is now assistant professor in Pakistan, who did very, very nice work based on also inspiration. The antenna at the left is really inspired by just shaping and exploration and the shaping of the material to make appropriate antenna radiating 360-degree, covering the band 1 to 10 gigahertz with very nice performance. And we got a patent about that because when we have analyzed the competition, we found nothing that cover all these kind of bands with this compact volume of antenna with very basic material, very inexpensive material at the center millimeter wave frequency at the end at the right. What we have here is very original work, okay, and this work developed like maybe 6-7 years ago. This is antenna to capture solar energy. So it's an energy harvesting using antenna. At that time, where we have started that thesis, nobody believed on that. We had a lot of difficulty to publish had a lot of difficulty. It was very challenging to publish, but the end we have succeeded to publish. Now it's a product. It's commercial, because the thing that we have thought about, it was like looked very, very very early stage or very difficult to do, and we had it was very difficult to make antenna at that size. We did the collaboration between King Saud University of Photonics and University of Rennes University in France, and we have succeeded to just make like very initial demonstrations of the principle that we can really get through the antenna, very small nano antennas, okay, to capture the wave or the optical wave, 1.5 micron, etc. It's very difficult to capture, and even when you capture, how to get a DC current out of that, how to get energy out of that, it's very challenging. But the guy who is Walid Sethi did very, very nice work, and he was very resilient. It's very important for a PhD student to be resilient, and for his advisor also. So now I will talk about few research projects that maybe I should check the time.
Yeah, Professor Fatad, I was about to say the same thing. Maybe I would appreciate if you can say conclude in the next, say, 5 minutes to keep up with our schedule.
Thank you so much.
Thank you.
Okay, because I am a good professor, I know I have no limit about the time. Okay, sorry for that. We are all good professors, but we don't count time. What we are engaged for is just to make people working well and making nice research. That's it. So okay, so I will survey quickly the research made with Professor Salah Shibili in the Photonics. We did very nice work. We are very proud of this team. Also, very few individuals, but every individual, every one of them is a champion. We really succeeded. I'm proud that we have developed champions. We don't have hundreds of students. We did not advised hundreds of theses, but every one of them is a champion really in his access. So okay, I will try to go faster. This project is okay. The evolution of technologies now, since many years now, is working on SDM, and most of the work of the team is using SDM in making fibers and specialty fibers with high performance of space division multiplexing. This project, this is a prototype we made with Agilent in Germany, and this is a real prototype. We have demonstrated at that time 0.5 terabit per second in a single channel. Pay attention, in a single wavelength, 0.5 terabit per second. And very quickly, we have increased it to many terabit per second. This is a real prototype developed by our students. And we don't have hundreds of people. This one is very interesting collaboration with KFUPM, with Dr. Zahid. Thank you so much for that opportunity that we have meet together and made roadmap of collaborations, and we have explored to use this quantum dash laser. If you look at the left, it's a quantum dash with like very noisy laser, and the start of our collaboration is how to transform that laser to a very nice, with very pure peak of laser. And this was, we experienced many solutions for external cavity based principles, and we have succeeded to make many publications and different settings of that. Here also is Majid Ismail, my former student, did very nice work. This chamber, we made that piece by piece design, etc. And this chamber emulates the dust storm in Saudi Arabia, the desert of Saudi Arabia. This is one of the, we spent more than 1 year just to build that, okay, build that in the right way. And we built the first version and second version. But this chamber, this investment in this chamber was very beneficial. We made like tens of papers out of that. You look for the OEM, and we also, the setup has been exploited by too many other universities, and people came to exploit the setup to make real experiments. This work for Lockheed Martin also about radar, we have exploited the photonics based and the same setting, same knowledge to make radars. Radars very special. Photonics radar are very strategic to the future, because in the future we have to detect very small objects like drones, very small objects, and these kind of radars we need photonics to make this capacity, this capability for detecting using radars very small objects and all the associated applications of that. This is our design, this is our prototype and working prototype. Very proud of that, with very limited resources again. This project joins the presentation, the second speaker, second speaker about automatic modulation classification. So because we have succeeded to make more than terabit per second per wavelength using high modulation techniques. So this project is to apply machine learning things to make to detect, evaluate channel impairments, to better detect the symbols, etc. This is the same project.
Professor Fatullah, I think we are unable to hear you.
The lab to make terahertz communication. Many hello, it's better now. Hello.
Yes,
hello?
yes, it's better now.
Professor Zahid, yes. Okay, alhamdulillah. Sorry for the interruption. It's a question of internet quality. We need more photonics for these networks. So this is an application also that we have built a few years ago about using Bragg ratings. Bragg ratings is exactly as introduced by Professor Tam in the beginning. So brake ratings to protect strategic cities and strategic infrastructure. It could be infrastructure, electric infrastructure. It could be pipelines. It could be anything. Okay, so this is, and we built that in our laboratory in King Saud University. This is also, these pictures show what kind of problematic we can address using fiber brake rating, and sometimes brake ratings is not enough. Okay, maybe a question a question for Professor Tam. Okay, this current project. So we use also machine learning methods to better detect images. Okay, better detect images for intrusions, etc. We use also to self-supervised transformers for background world representation without any. So here I came back to Tunisia in these slides. So they detect images applying with other. Okay, here is for healthcare and for the detection also of the behavior of people in surrounding. Too many applications using machine learning and artificial intelligence. This is also to detect another application, and so on. Thank you so much. I hope this was beneficial for the audience. Thank you so much.
Thank you very much, Professor Fatada. So any questions from the attendees or from the panelists? Okay, if not, then maybe we can move to our next speaker, as we are running out of time. Again, thank you very much, Professor Fatada, for your talk. And I would like to now welcome our last speaker, Dr. Yating Wang. And Dr. Yating, she is now an assistant professor at KAUST. Before that, she worked in Professor John Bower's group at UCSB from 2017 to 2022 as a postdoc and research associate. Her research is in the area of silicon photonics and special emphasis on integration of on-chip light sources for data communication, biosensing, energy harvesting, machine vision, and quantum information processing. She received a 2016-17 School of Engineering PhD Research Excellence Award in HKUST, and 2021 Clio Tingiri Innovation Award, and in 2018 Pierce Young Scientist Award, and very recently in 2021 OGC Best Young Scientist Award. And she was also selected as a finalist of 2022 Rising Stars of the Light, and she has published more than 60 peer-reviewed research papers, including 36 first author journals and 24 conferences. I think now I would like to give the stage to Dr. Wang for her presentation. Thank you very much, Dr. Wang.
Thank you, Zahid. So can everyone see my slides?
Yes, we can see your slides.
Oh, great. So hi, everyone. I'm Yating, an assistant professor in KAUST. So it's very nice to meet everyone virtually. And thanks to Zahid again for inviting me in this great forum organized by KFUPM and IRC CASS. So in this talk, I'll discuss integrated silicon photonics with on-chip lasers for optical sensing and communication applications. So first, I will give an overview on silicon integrated photonics and discuss my latest research achievements in high-performance quantum dot devices, mainly lasers integrated on industry standard silicon substrate. Then I'll discuss the integration scheme that have been explored to integrated quantum dot devices on silicon platform with the aim of process simplicity, high device performance, and commercial viability. And finally, I'll end with a conclusion on future perspective in incorporating these photon integrated circuits with on-chip lasers for different applications. What is integrated photonics? Integrated photonics is an emergent branch of photonics in which waveguides and devices are fabricated as an integrated structure onto the surface of a flat substrate, so allowing for the improvement in performance as well as a reduction in terms of size, weight, power consumption, and cost. So previously, the photon integration circuit has been entirely based on indium phosphide and it is 3-5 materials. But now we are switching to silicon. We're making photon integrated circuits the same way as electronic integrated circuits are made that can leverage from the most advanced CMOS processing with low price, high yield, and good thermal and mechanical properties. So the big demands today of data centers, particularly for artificial intelligence and machine learning, as discussed by the previous speakers, will continue to drive the need for faster applications and computations in the next decade. So this data traffic is projected to grow at a 25% compound annual growth rate for the next 4 years. So now the 3nm chips will be volume next year by TSMC for Apple iPhone and Macs, and 2nm chips will be available in 2025. And Broadcom's roadmap has a split chips going from 51.2 terabit this year to 102 terabit in 2024 and 205 terabit in 2026. So this will all be the economic driver for silicon photonics, getting into much higher capacity in the future. So there have already been a variety of photonic devices being put on silicon, including the low-loss waveguides, modulators, switches, detectors, MEMS, and nonlinear materials. And the foundry efforts across the entire world, especially in North America, Europe, and Asia, are quickly pushing the commercialization and wide deployment of silicon photonics with good thermodynamic properties, extremely low-loss waveguides. We're talking about 0.03 dB per centimeter loss waveguides, and excellent optical confinement, and the 300mm wafer scale, high scale processing, and high volumes and low cost. So this increasing number of players are now in the race of silicon photonics. For example, Intel's 100G transceivers based on silicon photonics are now in volume production, and Cisco is currently simplifying the 100G pluggable optics and beyond, and occasionally engaged for coherent silicon photonics. AIM could provide wafer scale test, assembly, and packaging for silicon photonics chip manufactured in the 16nm node, and global foundries are working on the 300mm wafers. However, at the same time, silicon is a kind of a bad material for photonics. So devices made from silicon and germanium can only cover modulation and detection for wavelengths around the near infrared, but are not suitable outside that range. Silicon is reciprocal, so you cannot make isolators and circulators from silicon materials. Additionally, silicon is indirect bandgap, so they are not suitable for making high-performance lasers or amplifiers, and actually the only demonstrated laser in this kind of material system have order the magnitude higher spectral current density than what can be achieved in this direct bandgap 3-5 materials. As a result, to overcome the inherent limitations of conformal materials for gain, efficient modulation, and detection at wavelengths outside the inner infrared, requires we incorporate the 3-5 materials with the silicon photonics platform. So to integrate 3-5 lasers onto the silicon substrate, the first generation of this hybrid integration fabricate the 3-5 devices and the silicon devices separately, and then mount the 3-5 dies on top of the silicon photonics dies using external coupling. So one obvious advantage of hybrid integration is it has the capability to optimize the active and the passive separately without sacrificing for process compatibility. However, this optical packaging with optical alignment often occupies over 90% of the total cost, and the efficient optical coupling of the 3-5 to silicon photonics waveguides usually relies on alignment with precision in the lower micrometer or even sub-micrometer range, leading to large footprint and very limited scalability. So another approach, heterogeneous integration, can actually bound this unpatterned 3-5 thin films to the silicon wafers at the early to middle stage with a coarse alignment, and then define the device by lithography on the full wafer scale. So as a result, the overall efficiency is very high, reaching coupling loss lower than 0.5 dB per interface. And with the chip maker Intel, this device was already used in mass production lines after simply 10 years of its demonstration, and is now generating over 1 billion of revenue nowadays. In addition, this technique can not only offer an elegant path to include 3-5 lasers onto the silicon photonics platform, but also makes it possible to flexibly add different functionalities, different materials onto the same chip, despite the material incompatibility. For example, the indium phosphide materials for telecommunication, gallium arsenide-based materials for 850 nanometer VCSEL, and lithium niobate for modulators, some InGaAs materials for photodetectors, silicon nitride, silicon oxide nitride for ultra low loss waveguides, and the YG materials for isolators. However, the associated technical complexity is still considerable, in particular with the very stringent requirement and ultra clean and extremely smooth surface before bonding. Moreover, the use of 3-5 substrate for the laser growth can be costly, and that imposes a limit on the maximal bonding size set by the largest available 3-5 substrate, which is around 200 mm for gallium arsenide and 150 mm for indium phosphide, which are much more smaller and much more expensive than the silicon counterpart. So considering the 3-5 substrate cost, monolaser integration through direct epitaxial growth is a more economically favorable option and can also provide the best natural heat sinking for laser operation. However, there is fundamental material difference between the 3-5 and the silicon during epitaxial growth that can generate high density of crystalline defects, including primarily the threading dislocations, stacking force, and antiphase domains. So these defects can act as non-radiative recombination centers that grow with the device operation into this dislocation network, and finally large network of dark line defects that degrade the device performance and shorten the lifetime. So while people has been trying to grow the quantum well lasers directly on silicon in the early 1980s, and actually they have got this pretty nice results in terms of special current, light output power, and external quantum efficiency. And so this kind of performance are almost comparable to native substrate performance. However, if you look at the aging test, the maximal device lifetime is less than 200 hours, like in spite of like decades of research, even with very low TDD and even with very time-consuming growth, even with the off-cut silicon substrate that is not CMOS compatible. So in this kind of scenario, how can we improve 3-5 lasers on silicon by orders of magnitude? So the strategy here we use is to deal with the active region, and quantum dots can be used instead of quantum wells. So what is quantum dot? The quantum dot represents this zero-dimensional article in a box-like quantum confined structures that can be formed through the self-assembly process using indium arsenide and gallium arsenide layers. So due to this three-dimensional confinement of carriers, a complete localization of electrons and holes can ideally give rise to the sequence of delta function density states, possessing analog degeneracy. As a result, quantum dots can promise a lot of performance advantages over its quantum well counterparts, including its high temperature tolerance that allow robust CW operation up to 220 degrees C and low special currents that is capable to support very low energy consumption. More importantly, for line width enhancement factor, or we call alpha factor. So the typical value for quantum well is around 3 to 5, but quantum dot is 15 times smaller. So from this scaling factor, you can see that the critical feedback level for coherence collapse is closely related to this alpha factor. And quantum dot has over 50 dB increase in its value compared to quantum wells, such that even with 90% of the light reflected back to the laser, so the optical and RF spectrum still shows no coherence collapse. On the contrary, for quantum well devices, complete coherence collapse will happen even at a very low feedback level of -25 dB. So this kind of property is very important to data communication system, because with this reflection tolerant quantum dot active region, you don't have to add isolators into the system to block the undesired reflections, which is bulky, expensive, and can greatly complicate the packaging and as additional insertion loss. In addition, for a carrier diffusion lens, the typical value for quantum wells is around 10 microns, but quantum dot is 10 times smaller. So in the case of relatively high spreading dislocation density, so we are talking about 3e to the order of 8. This is a very, very high defect density. But the carriers in the quantum wells, they are free to move around with the plane of the well, and they can encounter a defect before we combine radiatively. But in a quantum dot, since every quantum dot is quite locally trapped, and the chance of carrier mitigation to dislocation and be trapped by the dislocation trap state was greatly reduced. So, for example, if you see this red point refers to the defects, and this yellow dot refers to the quantum dot, and even with this very high spreading dislocation density, because the dot density is still more than 2 orders of magnitude larger, and because each dot just stays at its position, they are independent of each other. So one dislocation line can only kill one or few dots, and the majority of the dots are not affected, so device can still work efficiently. So this much improved defect tolerance gives rise to record-long device lifetime on silicon. So while I mentioned that the maximal lifetime of quantum well lasers grow on silicon has only 200 hours after several decades of research, our generation 1 quantum dot device already show lifetime of 800 hours at 30 degrees C, and our most recent results show median hour extrapolated lifetime at 80 degrees C. So this is a kind of a remarkable improvement compared to our first generation of devices, and also orders of magnitude longer compared to any previous lifetime test of quantum well lasers epitaxially grown on a silicon substrate. So there is a lot of recent progress of quantum dot devices grown on silicon, such as the sub-wavelength optically pumped micro disc lasers, the sub-million special electrically micro ring lasers, this couple cavity tunable lasers, this high-speed DFB lasers, this isolator-free system demonstration showing a path towards high-volume, low-cost transceivers that can be scaled to beyond 1 terabit per second, this 20 gigahertz molecular lasers with high channel count and excellent RF performance, this high gain, high saturation output power semiconductor optical amplifiers, and ultra-low dark current photodetectors, which has dark current 5 orders of magnitude lower than the state-of-the-art germanium on silicon photodetectors. But in addition to improvement of material quality and individual quantum dot device performance, we are particularly interested to achieve the low loss active passive coupling of 3-5 with the silicon waveguides, so that we can form a full integrated photonic circuits. And the most challenging part here is that we need to change from the indium phosphide based quantum well epi to gallium arsenide based quantum dot epi that needs totally different material systems and different device design and process optimization. So here the schematic showing the quantum dot laser integrated on the SOI substrate consisting of this hybrid 3-5 active region coupled to passive silicon waveguides. So the process starts with the passive waveguide process and the subsequent wafer bonding and the substrate removal, and then etch the 3-5 mixer precisely down to the end contact layer and keep the etching depth uniformly across the whole wafer. So for this step, a lot of process optimization was devoted to achieve this smooth and straight side work, and so that we can get this very nice 3-5 taper. And after this P-MESA paddling, and then we pattern this lower N gas contact tapered in a separate shot transition, and then we put this metal stacks as contact metals, and the device was passivated, and the via was opened for a probe metal. So the laser shows a special current of 4 million, sample saturation of 60 dB, CW temperature of 75 degrees C. But what I want to emphasize is the modulation bandwidth and the line width. So as you know, a very high modulation bandwidth has always been recognized as very difficult to attain for quantum dot lasers. So actually the best reported value on native substrate is around 10 gigahertz. And that's been using a very short cavity and with a lot of treatment. But here we got a record high value of 13 gigahertz achieved with just a polished faces and with these very long cavity devices. and which means there still remain a lot of room to further improve it, reduce the cavity length, add a permeable facet coating, deposit the metal on a thick dielectric or low capacitance, etc. And for laser line width, which is closely related to alpha factor, due to the 15 times smaller alpha factor in quantum dots compared to quantum wells, we got 26 kilohertz, which is an order of magnitude lower compared to the typical solitary quantum well laser line width, which is several megahertz. So again, this table compares the device performance of this work and previously reported work, which I want to show again that laser with a silicon waveguide can significantly outperform lasers without a silicon waveguide in terms of line width, bandwidth, side-mode spatial ratio, etc., which we are very excited about, as it shows a synergistic relationship between the unique capabilities of 3-bit quantum dots and silicon, allowing for not only reduce of cost due to the economic scale, due to the larger, smaller substrate, but also much better device performance, exceeding what is achievable with purely 3-bit quantum dot devices. So when you put lasers on silicon, you not only get a better substrate, you also get better lasers. So following this direction, we now cooperated with Intel and is using Intel's 300mm silicon photonics platform to pattern the passive part and to be bound with our quantum dot epi. So the heterogeneous integration process has been very successful in Intel with mass production lines. So by changing out the bonded quantum well application material for quantum dot on silicon substrates, there will be substantial opportunities to build upon what has been achieved through heterogeneous integration to both improve performance and reduce cost. And in addition, this kind of dense device integration with on-chip lasers in silicon photonics will be ideal for any applications that have high volume needs to be scaled rapidly. So the use of silicon photonics in datacom is well established. So Intel, is having $1 billion business doing that, and many other companies are also actively involved. And with the foundry efforts from TSMC, Global Foundries, AIM, and Tower, there will be tons of opportunities open for other applications as well, LiDAR, gyroscopes, the spectroscopy, for example. So telecommunication, as Acacia has demonstrated, is a second high-volume application with the superior performance from silicon processing really helps. And the lithography in a 65-nanometer process is far better than a typical indium phosphide foundry. And furthermore, silicon photonics already show promise as a platform for quantum computation, and quantum dots show promise as a source of entangled single photons compatible with the proposed computation schemes. So this kind of related research is still in the development stage. But if quantum dots can be integrated in silicon photonics or for classical applications with established process, that it makes sense to grant an extra consideration in designing future quantum computation platforms. And for neuromorphic photonics, which we are particularly interested in. So the current approach of fiber cup packaging is the most straightforward way to get light into the chip. But in the future version, especially spiking neural networks, on-chip laser source would be required so that all optical signals will be confined within an integrated circuit package for the efficiency, stability, and scalability. Another general application is optical LiDAR. So although the cost must be smaller and the complexity must be large for an optical phase array, and shifting the beam around needs to be matched to the electronic drivers to control the optical phase array. So it becomes more important to have chips on the same substrate for 3D integration. And finally, for photonic biosensors with integrated light sources, the price will be significantly reduced and the size will also be significantly reduced, which is very important for polymer devices. So again, by leveraging all these attractive features of integrated silicon photonics and the advanced PDK from Intel and this heterogeneous process, on-chip laser will revolutionize these applications for substantial performance gains, green solutions, and mass production. So to conclude, we have achieved a lot of progress in the last 6 years. Laser integration for silicon photonics is definitely the key to advanced photonic researches and the solution that can best leverage the economies of scale while maintaining the highest yield will be. So it's a global race, and I'll see that Intel is leading the commercial end of it, and we are looking to work to lead the research end of it. And finally, and most importantly, I'd like to thank my integrated photonics lab in KAUST, and also my postdoc supervisor, Professor John Bowers, and the UCSB group. And also I'd like to thank all my collaborations, particularly Haisen Ro's group at Intel, for contributing so much to this work. In the meantime, I'd like to, since there are many KFUPM students, I'd also like to use this opportunity to share the news that PhD student fellowship positions are now available in my group for 2023 admission. And we also have KAUST Global Fellowship programs open to postdoc applications. Successful applicants will get access to the state-of-the-art research to do semiconductor research. And also, you know, KAUST ranks first in the world. Okay. So KAUST ranks first in the world for citations per faculty in the QS world ranking, and top 20 in the world of fastest writing universities. And this is a beautiful place with RASI just steps away. And we provide workplace lead environment with the state-of-the-art fitness facilities. And we are also very international. We have probably we rank first in the percentage of international students and international faculty. So you will enjoy the diversity and international university community. And also our alumni are contributing to industry and innovation around the world, with 65% employed in top industries and 23% in academia in great institutions. And before you make this big decision, we also offer some short period intensive camps and schools during specific seasons to help you practice and get some skills and introduce you to the research project. So we have this microtronics winter camp and a photonics summer camp. And so if you're interested, please send your CV, your research plan, and transcript to my email. So I expect the students to be very self-motivated, have creative ideas, and are willing to tackle important problems. And I'll be happy to chat before your applications. So yeah, that's all. Thank you so much.
Thank you very much, Dr. Won. Let's open the floor for any questions. So any questions from the attendees? You can raise your hand and we can allow you to talk, or even from the panelist. Not much. Maybe, before concluding, if I may ask one question, Dr. Yating. You have mentioned a little bit about, the quantum communications, right? Mm-hmm. So would you be able to comment more on, how this quantum dots on silicon would help enable the single photon or entangled photon sources? And is it possible to have an electrical driven type of such sources in near future, or is it already been established?
I see. So in terms of doing quantum, there are always different approaches. Like the US and Europe have different voices, and people argue for years. Like the US thinks like they want to do quantum using silicon carbides on things like that, and in Europe things we like quantum dots. So from our side, I think if you can using quantum dot to do quantum computation, the really main challenge is really how you can get this very uniform quantum dot for single photon source. So because generally the quantum dots are grown by self-assembled process. We call this SK mode process. So in this kind of process, it's very difficult to control the dot. So it's very difficult to get uniform and uniform and identical dots. Especially, it's very difficult to reduce the dot density. So increase the dot density is difficult, but to reduce the dot density is also very difficult. But how can you get this very uniform dot growth, and how can you make the density very low so that you can just filter out the exact dot you want? And for single photon source, I think that's the main challenge if you are pursuing this quantum dot approach. That like if you're in US and followed by the US government, then you have no choice. You can just switch to another direction using spin carbide something. So that's a totally different story.
Okay, thank you very much, Dr. Wong. This actually concludes our second session, and I would like to thank all our speakers for their great talk. Then we have just few minutes left. We have a very short panel discussion, in fact, very short one. So, I would appreciate that, maybe we can do the following. So we have Professor Tam here, Professor Fatazai here, and Dr. Wong here. We have our graduate students here. So maybe, on behalf of our committee, I would like to just pose a question in front of the speakers, and maybe the speakers can provide their thought maybe and summarize it in a minute or minute and a half. And after that, we will conclude the talk. So, the question, that we have is, again, for a green, secure, and a resilient digital society of the future. So what research directions in photonics would you prefer to recommend to our young generation of researchers in this region, which is Middle East, as well as around the world? So this is the question. So if I may repeat again, for a green, secure, and resilient digital society of the future, what research directions in photonics would you prefer to recommend to our young generation of researchers in this region and around the world? So maybe I would like to start with Professor Tam.
Okay. Obviously, I'll talk about, I would recommend applying AI or machine learning to a photonic sensing network. And I think there's a lot of potential there, because even now, if you look at most of the paper, they're using fiber optic sensor, for example, like FPG sensor. Now, one thing I did not mention about the power of an FPG sensor is really that it can measure virtually any parameter. We use it to measure physical parameter, biological parameter, and also chemical. Now, there's actually one slide that I only showed the picture, but I didn't go into the detail. What we are doing now is actually we make spatialized fiber. We make fiber in a spatial type of polymer. And we design the fiber depending on the particular application that we're looking at. Now, one of the exciting example is I think probably two exciting example using fiber grading sensor is in the medical area. I think there's a lot of potential there. Okay, and also is something that is really needed in the society. So one of the application is actually we are collaborating with a hospital and also the University of Melbourne, and trying to develop the so-called smart cochlear implant. Okay, now there are actually many people in the world suffering about hearing loss. Okay, some baby actually when they're born they can't hear, and some because of the accident. Okay, and they hear damage and they could not hear. And the only solution is actually implant cochlea. Okay, so you implant sort of like what we call is the cochlear implant Now, what the doctor is doing now is the surgeon can do is they actually have a drill 3 holes, okay, behind your head. And then they insert a tiny implant in there. Now, the problem with that is it's a very effective solution, but it's very costly. So what we're trying to do is we're trying to reduce the cost by actually embedding sensor inside these tiny cochlear implants. Okay, so that's never been done before. And if the cochlear implant, what we call a smart cochlear implant, if you have a sensor, then it will significantly make the operation easier. And obviously, it will have a much higher success rate, and the cost will reduce. And then more people can benefit from having this so-called smart cochlear implant. So this is one area I think we just started. Not many people working on it, and I think it need a lot more researcher, and also it need a lot more like funding to invest into it, and more students or perhaps professor looking into this problem. This is, I think, it's a huge problem, and if it can be solved, then many people can benefit. And I think operations, something like that, probably costs like about 200,000 US. So not many people can afford it at the moment. Yeah, it's a very expensive, very delicate surgery. So hopefully, once you can implant a fiber sensor in there, you can significantly reduce the cost. Now, another area they're working on is actually in helping, looking at the bone. Okay. One, if someone have an accident, they have their bone replaced, then if you can actually monitor the healing process, it can also help a lot. But then that will also require a lot of research, actually developing a spatial fiber that can go inside the body, and then develop this the entire monitoring system that can be embedded inside the body, okay, to monitor the healing process using IoT. And this is actually something we're working on. So we're trying to miniaturize the entire interrogator into something that is very small that you can embed under the skin. Yeah. So that also can benefit a lot of people. So there are many areas. So I'll just stop there and let other speaker share their views.
Yeah, thank you very much, Professor Tam. Now maybe I will open the floor for Professor Fatala if he can share his opinion in the next 1.5 minutes.
Okay, thank you, Dr. Zahid. Okay, I would not suggest necessarily specific directions, but I would say I will underline specific values. The value of open science. It's very, very important to share our knowledge and science with everybody. It's very important to increase the accessibility to science, to the right to technology and to knowledge to everybody around the world. Okay, so the value of sharing science, the value of passion also. So I ask students to be passionate by science, not publications. Forget about publications. Get the time to do nice work where you feel yourself flourishing. You feel yourself happy to make that work. And maybe in terms of tools, I think the quantum age and quantum paradigm is not now obvious, and it's very necessary to work on and consider it in all different aspects. Okay, also the artificial intelligence, and all the bricks or the puzzle pieces in artificial intelligence. It affects everything. It's not just the communication level, but also device, and also as Professor Latin presented, also the device of the materials, the future materials, the future everything will be based as the mathematics have played a very strong role in everything, in making everything artificial intelligence will take a lot of that role. So it's very important. And try just in mindset to have, okay, serve people, serve what people need, okay, not what the industry needs, okay. Serve people, think about people. By the end, you will make your project and you will find your specific road. Maybe you will make your startup. You will make your own success. But I think values is first, and the cutting edge technologies and tools is second. So artificial intelligence, quantum agent, quantum paradigm, and good knowledge sharing. That's it. Thank you.
Thank you very much, Professor Fatada, for the nice message. Dr. Yating Wong, maybe if you can say comment.
Yeah, I agree every word Professor Tan and Professor Habib talk about the importance of AI and machine learning. And I want to add that for saying that in world of AI and machine learning, they took huge amount of computing capacity. And for data centers to handle that, they need the transition from electronics to photonics, which is simply due to the fact that the capacity of an optical fiber is 1,000 times that of an electric wire, and the signal loss in a fiber optics is about 1,000 times lower than electronic wires. And to make this transition from electronics to photonics possible, we have to do the integration the similar way like how electronics win, like 3nm chips is involved last year by TSMC in iPhone and Mac, and 2nm chips will be available in 2025. So to make all this possible, integration is the key. And photonic integration previously has been entirely on indium phosphide. We're talking about this 2-inch or 4-inch small wafers to be processed in the foundry, and this kind of three fiber materials. But now we are switching to silicon. And we are making photonic integration circuits the same way as electronic integration circuits are made. So I think it's a very interesting research direction, and it's a global race. So I will say that Intel is leading the commercial end of it, and we are working to lead the research end of it. So again, AI is very important, and machine is very important. They make us a better world, and photonic integration are the things that make AI, make machine learning possible.
Thank you very much, Dr. Wong. So I think with that, we will close our panel discussion. And Professor Azadeen, if you can turn on your camera, maybe we can have one nice picture of all of us. Professor Azadeen, if you can hear me. I think he's busy. Well, anyways, Dr. Khurram, maybe you can take the lead in concluding the forum.
Thank you very much. I would like to thank all our distinguished guests and speakers. It was really very insightful. We really enjoyed your talks, very informative, and I hope our students, the grad students, have got benefit out of it, and hopefully somebody will take a work from one of your works that you have talked about and work on it in future, and could be our future professors and leaders in the field. So thank you once again, all the speakers, for your time and patience with us. Thank you very much, and hopefully see you around in some conference, meet you somewhere, or maybe virtually again, hopefully. So thank you very much, all the speakers and the guests and the students. Hope to see you again. Okay, bye.
Thank you very much. Well, just 1 minute. Let me take a picture, and then
Okay.
and then we will stop. Okay. Okay. Thank you very much. Just give me a minute. And let me just verify it, please, whether I have got the picture or not.
Please share with us.
Okay, thank you.
Otherwise, it's difficult. We will not be able to have picture together. Just 1 minute. Yes. Thank you very much.
Thanks, guys. Thank you.
Thank you.
Have a
Thank you
nice
very much.
evening. Bye.
Bye.
Bye-bye.
Bye-bye.